And I have one mission today. My mission is to convince you that you're going to become the ambassadors of a revolutionary change, which is going to start from New Zealand. It's going to invade the world in the same way that New Zealand has been leading earthquake engineering in the 60s and 70s. Christchurch via Canterbury, via this earthquake, unfortunately, can be the opportunity to again be leader in the world. And it's going to be a bottom-up revolution. And you're going to be the one making it. Now, there are probably a few hundred people over here. You have basically your challenge is to talk to at least 100 people each. And the mission for me is that you're going to go home and you're not going to talk anymore about what type of magnitude it was. You're going to say, what type of technology are you using in your house? It's going to be new questions, not anymore which direction was the earthquake is going to happen. The answer was, who cares? I have the best technology that I can use to not be too much bothered about it. So it's going to be a mind brainwash that I'm going to give it to you. And because you're going to be brainwashed, you're going to talk to your colleagues who did not come today, and they will not understand what the heck you're talking about. They were going to ask you, are you actually speaking my same language? You say, no, probably I'm speaking Italian, but the volume is low. And one of the best examples that I'm talking about, reinforced concrete buildings, is San Telmo. San Telmo, just to make a story about a building that I think is absolutely beautiful, was. And after September, there was the possibility of saving that building, strengthening that building. We were working on it. I'm going to tell you something not too much into detail about how it could have been possible to do something. February earthquake came over, and then at that time, it was not anymore cost efficient in a way to preserve that building, but it's something that I would like to tell you about. So I would like to just demystify some prejudice, myth, fallacies that you might have been having for a while, and then give you some truth. Now, the truth can be good, can be bad. It's the truth. You take it, but I told you at the end of this lecture, you don't think about the bad. You're going to think about only the opportunity for the best. And these toys, these magics, are going to help me in convincing you. Unfortunately, I should tell you honestly, I've been at least for the last, since I came over to Canterbury University in 2002, I've been giving lecture courses on retrofit of existing buildings. And in my lectures, in 2002-03, the last example that I was using was 1999, a very massive earthquake that happened in Turkey. And there was a humongous amount of victims. And there were thousands of buildings of this nature, reinforced concrete, this is designed until the 1950s, 60s, 70s. Please remember that pre-70 is actually a quite fundamental milestone in earthquake engineering. And then, unfortunately, in 2009, my country, first country, I didn't tell you, for some reason, someone convinced the Queen to accept my citizenship application, so I became a Kiwi Italian now. And my kids were born over here, so I have now two countries. This Turkey, I will show you this country, that have been affected within 2 years by severe earthquakes. L'Aquila earthquake, someone have heard L'Aquila, the pronunciation is L'Aquila earthquake, was something that could have helped in understanding a lot of, can still help in understanding a lot of what happened over here. Just to give you a little bit of analogy, we came back from that earthquake, and then I decided to spend more time during my sabbatical year. And we came back telling to people that there was something absolutely unusual. A main city, maybe it will ring your bell, déjà vu, a main city struck by an earthquake which was just underneath the cathedral. The epicenter was just underneath. And that gave a huge punch into the medieval center with a vertical acceleration which was so high. Does it ring your bell? And people said, it doesn't make any sense. We don't have vertical acceleration. We have an alpine fault far away. There's no way that we can have a vertical acceleration. And I'm sorry for your country, we understand, but you're dealing with the structure over there which are old, reinforced masonry, very vulnerable. And I will say, yes, but it's not that's correct. We do have in Italy many reinforced concrete buildings which are similar to the one in Turkey, or similar to the one in US, Japan, California, sorry, still US is, but in California they think that there are more than US. Canada, South America, and New Zealand. For how good New Zealand was in 1960, 70, 80, 90 in earthquake engineering, still I'm going to show you that this is nothing different. And now, unfortunately, we had the confirmation. So 2010 came over, September the 4th, and that was a bad news, that was a good news. That was half a story of success. It was half a wake-up call. For too long, probably, not enough, 6 months, we've been thinking about the story, the success story. It was good to say big 77.1 event, that magnitude earthquake around the world would have caused much more, many victims. There was something else which was missing, and it was the time of the earthquake, many other things. Unfortunately, February reminded that there was something missing. So you people are here because there's something that you can't accept. You can't accept society. As a society, you cannot accept, and I'm part of that as a citizen and a father and a husband and something else, as a friend of people, that what we got in town is the best that we can do in 2011. Doesn't make any sense. There's an earthquake, we're getting victims, and the typical expectation of the society are what we call the 3Ds, no death, obviously. The first thing that you can avoid, you must avoid, is no victims. And for new design, it's something that is achievable for new design. For all design, all buildings is a different story. We don't want to have collapse, but then you people, everyone is asking for something else. Is asking that for a normal earthquake, a big earthquake, a maximal credible one earthquake, it doesn't matter, still an earthquake is. It did happen. The level of damage that is going to occur should be the minimum that is enough to reduce the direct cost of repairing the house. But then you're asking for something more. You're asking to have basically no business interruption. And everyone is thinking that in a modern country, like New Zealand is, we should be able to give that to the population. So how comes that in best international practice and current best code in the world, and New Zealand is on those top 4, which is US, Europe, Japan, and New Zealand, are considered the 4 best code in the world in terms of earthquake engineering. Now, let me tell you something that probably no one have actually communicated to you, the truth. The truth is, in international code, because of a sort of an implied agreement with the society, with you people, you were part of that agreement somehow, and I will try to explain how. When you get a big earthquake, and this is the big one, frequent earthquake is going to happen every 50 years. So basically it's going to happen. It's something, it's a probability, but it's a small type of shaking that you're going to feel in Wellington any time, sometimes over here from Milford Sound. You would like to have a green tag. We're going to disclose these magic things of the green tags. The green tag means basically with a moderate earthquake, you're expecting fully operational building, so you're able to go back to your building without too much trouble, saying keep on working. As soon as the earthquake becomes a little bit bigger, something which is going to happen with less frequent or less probability, then you're going to have a little bit of a trouble. So some damage, still operational, so you're still able for a few days out of your office, out of your house, is going to be yellow type of damage. For the design level of earthquake, which is what we typically accept everywhere around the world, the design level of earthquake is defined as that earthquake which can come approximately every 500 years. Means nothing. A better way of saying it is that it's going to have a probability of occurrence of 10%. It can occur 10% within the lifetime of your structure, 50 years. What does it mean? Let me say in a different way. It's a little bit harsh, so in a way I'm not too happy that we are recording this presentation, but 10% means I'm going to have a bullet over here, 1 out of 10, and I just shoot 10 times. Are you going to be happy? This is the reality of what does it mean, earthquake standard, for which a big earthquake, 500 years, 10% of probability of happening, is going to happen, can happen, 10% can happen, is going to happen, maybe not in our generation, but later on, is going to give you what? A severe yellow, almost a red tag. You see that? It's part of the code. For a basic objective, which means a normal building, not a hospital, this is part of the acceptance of performance-based design, meaning the bigger the earthquake, the more damage we are going to have to accept. That was not what you thought when people told you about earthquake proof, right? And this is exactly what we're going to try to demystify. For a very rare event, which around the world is conceived to be internationally an event which can happen every 2,500 years, doesn't work like that, can happen with a probability of 2%. Small, 2%. How many people are here? Again, I will have 2 bullets for 100 people. 2% of probability of occurrence, you're going to be severely red. Severely red means you're just, the house, the building, is going to be just there. Now, did you know that? No. So there's a mismatch. The mismatch is that basically, for how much I respect my job, which I love it, we tend to teach in class. And earthquake engineers, or engineers in a way, are, I'm not saying the worst communicator, but basically the venue where we're typically talking into are venues of conferences internationally. Engineers and engineers preaching to the converted, preaching to the converted. Okay, so we're telling to each other what's going on. Thank you very much. Does the public know about it? Does the political decision-making people know about it? So today, you're going to now know that this is part of the code, provided that we take the code as we understand that the code is a minimum standard, very important, it's not the target. Who told you that you have to use the basic that is written in the code? Who told you that you cannot ask for more? There are different ways of having a car. A car can have something with 4 wheels and something to steer and possibly brakes, maybe. And this is a car. And there's another higher level of cars. Okay, that's a legal car that passed the warrant of fitness. You're still wondering to which friend did you go to get the warrant of fitness? Because impossible that the car could have passed through. It legally passed through. But then there is something a little bit better that is a much more safe car. And the point is, why did we all the time choose the cheapest? And if I can make, with my now new power of being a citizen of New Zealand, an application to the Queen, I would ask, can you please cancel from the vocabulary in English the terminology that is cheap? Just take it off. Take out of the vocabulary cheap, should not be used, must not be used. Cheap should be substituted by something which is just down a few lines called cost effective. So don't from now on anymore think about cheap being the target. And I'm the same person like yourself entering a supermarket and buying the discounted one, the discounted products. Fair enough. So what we are going to target now is a discounted best, such that people are going to get the best for lower prices. And I'm going to discuss what it is. So just knowing, you understand now tagging, and you understand that under a decent earthquake, the type of level that the code is protecting you by is to have repairable yellow, irreparable heavy yellow, so basically a not repairable building under a severe level of shaking, which mostly was between September and February. That's the reality of facts, unless we do something else. Now, fallacy. The code is not a target, the code is not the goal. We must not, you must not accept someone to propose you the minimum standard, like when you're shopping around for anything else. You must know about better performance, new products, what is available, and today we're going to tell you something which can do much better. The code is actually minimum by law. If you go lower than that, you're illegal. So why are we accepting just to be just that level up, the legality, can you say that? Or why don't we just do a little bit better and ask for a much higher level of performance? Now, the bad news, or the truth, is that by definition, what all of us thought about being earthquake-proof doesn't mean earthquake-proof. What you thought being an earthquake design structure, being that type of structure which you just can have a nice shaking and going out to check whether the magnitude gives some liquefaction or not, coming back to your house and being safe, doesn't exist. Sorry, or it do exist, but it's not what you bought. So what you bought is something which is earthquake-proof enough not to collapse, new not to collapse, but to be severely damaged such that it's going to be irreparable. So this is unfortunately the truth, provided that if you're going to stay on the minimum by law. No one is telling you that you can't raise the bar. We're going to discuss that. Now, question-answer. In order to avoid the problems with the microphones, I'm going to have a question-answer section, which is I ask the question, I give the answer. The questions is a frequently asked question. So thank you very much. Okay, so can you do something better? I'm sure that someone would have said, yeah, it's easy to tell us the bad truth. Can you do something better? And the answer is possibly, very possibly. Just ask. The second one is, thank you very much, how? The question is, how, if you raise the bar, this is going to be the revolution. And really the news that everyone, everywhere around the world, unfortunately, it took a major disaster to raise the bar. Unfortunately, New Zealand did not want to listen because you just don't think that is going to happen to you. We don't think about it. I myself, I did not have water in my house. I'm an earthquake engineer. I'm hopeless. I had a student bringing some milk to me because I have kids and he didn't think about it. I was just thinking about entering buildings without stairs. And that was more important than everything else, and did not have the basics, and so it's not going to happen to us. That's the perception. But because we know that it's going to happen, very, very likely in the next few months, now, what is the way of raising the bar? And the question and the suggestion is, don't wait for the government. We are typically blaming the government in Italy all the time, whatever is the government, Berlusconi and so forth, okay? So it's not them, it's us being the market, self-regulating, and not accepting to buy something which we are not thinking is good enough. And I'm going to tell you what does it mean. Now, there is another question that you're going to ask. Yeah, thank you very much. You can build and design a bunker, and it's going to be safer. But the answer is, you don't need to design a bunker. There are technology, which we're going to show you today, they're all here, which are going to give you that type of expectation and are going to cost less. Can you believe that? Are going to give you better and cost less? Can you believe it? I'm going to explain you the trick, the magic of that. Now, can we meet it? Yes. So we would like to be here. We would like to design, regardless of the level of earthquake shaking, September, February. So I don't know, it's quite interesting that from an engineering perspective, we are going to see things in a different way. There's going to be something happening tomorrow. Doesn't matter too much. Just use something that is going to take a big February, September, June 13 again, and keeping you in the repairable level. Okay, that's the target. Can we do it for the same price? Basically, it's shifting. You see, instead of being down here, up there, we are actually coming with a level which is a little bit better, and you can change that level. You can ask to someone, sorry, I like that car, but how much does it cost to just get a better one? And they're going to call you, oh, you got me. Actually, I was trying to give you the old stock that I had, and now you got me that there's actually better technology that I have to sell you for 30% of discount. So this is something that does happen, and we're going to discuss about how building technology has changed and how it was in the past. So just believe us when we are telling you that the famous 1970 is a milestone, is actually a threshold in changes in the way of designing buildings. And that was 1970, was ages ago, so something should have happened of the same nature. That type of revolution happened in the 1960, 1970, and it did happen in Canterbury University. It did happen in New Zealand. New Zealand was leading the world, telling that if you have a chain, and basically a building is a chain, you are going to have, by definition, a weak link. There's going to be something that the earthquake is going to find. That's part of the nature of finding minimum energy to just go through. So there is something in our body that is a weak link. If we can make the weak link, the link of the chain, the ductile one, so our weak link, my weak link, you have one, I have ankles and knees very, very brittle. I broke them so many times. So when I was going to the doctor, I was asking, can you please put a ductile ankle? What the heck are you talking about? I mean, I don't know. Something which is not going to break every single time that I just go over. I would like to have something which is going to be replaceable. As soon as I knock it in, my swelling is going to disappear immediately, and I'm going to have a replaceable ankle. Can you provide it to us? So you understand the point is that if we could make our links, the weakest one, ductile, this is going to at least preserve us from fracture. And that was the revolution in 1970 in New Zealand, where Professor Parker and Poli suggested that we are going to we designed the weak link to be where we want. I would like to have the weak link over here, and I'm going to work a lot to make my connection between the two elements the more ductile possible, something which can stretch nicely without breaking in a brittle manner. So the novelty was ductility versus brittleness, and everyone understands brittleness. Glass is hard. If you go over the strength, you're going to fail in a brittle manner. It doesn't matter how hard it is. There's going to be, by definition, all the time, a bigger earthquake than what we thought, and that unfortunately happened. That's why disaster happened, because there's always going to be something that we did not know. So the best way of protecting us from the unknown is actually to have something, a backup plan, which is going to give us a little bit of a possibility to go further instead of collapsing under a bigger than expected earthquake. This is what is taught in the world since the 1960-1970 called capacity design, which means if you do not decide to have a ductile type of mechanism, this is going to be your ankle breaking up over here, breaking up over there, which is going to cause columns breaking badly, are going to cause a collapse. And this was what the design philosophy until the 1970s in the world were. So anything that was designed before that was very prone, is still very prone, to have this type of collapse. We have seen these collapses everywhere in the world. Now, the best way after that, the new revolutionary way in 1960, 1970, which entered in codes around the world in the mid-70s, was to place ductility in where we wanted, such that our building can actually sway quite nicely without collapsing. And the better place to place those elements, those fuses, is not in the ankle and in the knee, is actually in the beams. These are the beams. If you have this mechanism becoming, imagine hinging, that's what happened, you don't collapse your building. Can you see that? There's no way of breaking your ankle at that time. So this happened in 1960, 1970. How can you spot it? If you see something with strong legs and small beams, good, approximately. If you see something with slender legs and a big body on the top, which is basically this type of configuration, So it's not that complicated, but imagine that in the 1960, 1950, the best engineers did not know enough to understand this type of situation. So at that time, they were doing their best up to what they knew. And this example, the issue of design standards in the world and in New Zealand. New Zealand was very, very good in improving and promoting new design standards every 10 years. So just imagine from a revolutionary approach, which is able to preserve a building from collapsing suddenly, then from there on, every 10 years, 1982, 1995, 2006, and now there's going to be a new code, things have been dramatically improved. What does it mean? Just imagine how much we would smile at looking Formula One. Obviously, I'm biased, so I think that still Ferrari is the best car in the world. So the 1960 Ferrari was absolutely fascinating, wasn't it? It was the best car. It was the fastest one. In the 1970s, wow, the evolution in 10 years was unbelievable. 1980, unbelievable. Now, 2011, we're looking back at those 1960 and 70, we are smiling. They did not know. Look at that. They were still using. And then think about our cars. Can you believe it? They did not know about seat belts or type of braking. So imagine what does it mean in terms of technology, 10, 20, 30 years of evolution. And so believe us that if codes have changed in every 10 years' time in New Zealand, every 10 years you are having a major improvement. And in 50 years from now, we're expecting people to look back thinking, oh, can you believe it? They didn't know. They didn't know that they will be looking at our technology in 2010 like an older type of technology. So in the generation, codes have changed, concrete technology have changed. So what is the mission today is to do the best that we can do today. The best that we could do in 1980, this is still a fantastic example that I'm still using. You can recognize the building. I prefer not to mention, but it's quite clear. This is an example, I tell you, I've been giving lecture around the world about precast concrete, and I still use precast concrete, this building, to show how fantastic this technology was for precast concrete. And this technology gave you the possibility of going through an earthquake, which I'm going to show you how bad it was from an engineering point of view. And it did do the job that was meant to do. So basically developed these famous plastic hinges. It developed a fuse within the body good enough that the building did not collapse and needs to be repaired. If you think that this earthquake was much stronger than what that building could have been designed in 1980, this building did brilliantly. But there was a gap of communication, a lack of communication. People did not understand, did not know, were not told by someone, because you thought, basically you agreed, that code means minimum standard and nothing else. So that did the job. If you see what type of damage we get in a laboratory, this is nothing. This is absolutely okay. Apart from some minor detailing that I don't want to go, it's a structural detailing. But in principle, this is not a massive level of damage. Can be repaired? Absolutely yes. Unfortunately, you have an insurance which is going to give you a full replacement. So what is the option of having a scratch on your car and going to be bothered by going to the panel beater or getting a new car? Get a new car. Back in Italy, we don't have that insurance, so we basically have to rely to the government, blaming the government for not coming down with billions of dollars to repair our cars. They're saying we can't afford it, so to replace our cars. They're saying we cannot afford it, so okay, I take a repairing. I can go with the panel beater. panel beating. Okay, so these things that have happened are actually the way of dissipating the fuse, the energy, and avoiding the collapse as prepared. Now, from an engineering perspective, first of all, dots means bad news if they are red. That's quite clear, even for an engineer. But apart from the dots and how many there are, what it counts really is not the magnitude. Now you know it. It's not the distance. We've been hitting hard, trying as much as we can. I'm very happy that we have someone from the press today here, which I can't find anymore. There it is. Because please don't use magnitude anymore. Nonsense. I can take magnitude 9 in Milford Sound. Now you know it. That is going to do not that much. In Christchurch CBD, you know it. I can take magnitude 6. I shouldn't say today under our feet is not good luck, okay? But that is going to be probably affecting us more. And the building counts, the building feels the shaking, doesn't feel the magnitude. Okay, so there is a way of communicating science which is important and is fundamental. That's why we are very proud and pleased to have the opportunity to talking to you people, because you are going to be the one making the revolution, not certainly us. We are going to provide you the tools, but if you were not convinced that the revolution can be made, so problems happen. February, September, June, many, many big shocks, okay? And now it's quite clear that the one in February had that L'Aquila push under the feet, which was very severe, more than something coming from far apart. And that's now quite clear that the Alpine fault is still there. Okay, it's going to come, that's part of the deal, we are designing for it, so we need to be aware of it. And all of those green aftershocks, they might have some consequence or not on our building, depending on different type of issues. From an engineering shaking point of view, from the building point of view, the building, the same building, which was in the CBD, basically felt something of this nature up north over there, a little bit bigger in the city center, massive, but there were no big buildings like that close to Darfield, okay? But then when it came about February, look at this. February, this is 1G, and this is more than 1G. What happened is that not only our body, you felt it. I keep on telling to the people in Wellington that were not down here, that yes, it was there, vertical acceleration. You can't believe how much it was there. It was pushing hard, we were bracing. And so if you are being pushed up, you can imagine that the building gets pushed up. Think in a different way. If you are skiing, that's the best example that I can give. And honestly, there's a lot of learning about vertical acceleration, which is a learning for the world, not only for us. If you're skiing and suddenly you go through a bump, what you get is you don't have the time to jump. You go through the bump, your legs are coming to your bodies, and you feel burning on your legs. So you get the axial load on your legs before you have the time to release the way up and jumping, right? That's what happened to the buildings. They get a bump. They were not skiing. They were just standing. And the piece came underneath, and they got pushed so heavily underneath that basically, suddenly, imagine more than 1G means that I'm quite a good unit for my students because I'm 100 kg. So I'm the unit. 100 kg is a unit. 100 kg in a square meter is a unit, 1 kPa. So it's quite simple for my students to remember how much is 1 kilopascal and 100 kg. So 100 kg on my legs will be becoming 200 kgs. I tell you, if you're not fit, and I'm not, if you give me another 100 kilograms over here, and then you start pushing me laterally, I'm not happy. I was not designed to be pushed laterally. My body was designed to stand gravity, and now you're telling me that horizontally, I will feel 100 kg in this direction. I'm not happy. What I will try to do as much as I can, because I'm an active human being, I'm not a passive builder, I will try to use my legs to control the displacement. If your tower was not designed to take such a huge forces, your tower is going to break the ankle. What a surprise. So what happened was way, way, way above what is written in any code. And that's important to tell to people. At the same time, this is an interesting graph. And this interesting graph, I want to spend a little bit of time because is what is written in a code, what the world is using to try to make this complexity, huge complexity, into 3 pages. Okay, these are going to be 3 pages in the code into how to design buildings. And those 3 pages are going to have 3 graphs, one of which is this one here. The graph is telling you the acceleration felt by the building, the acceleration felt by the building, You see 1G over there? Okay, so just follow that. So 1G is going to become, I will feel at this level 100 kg pushing me laterally. If I'm a taller building, and the period is actually representing how tall the building is, the taller the buildings, the more what is the period is telling you how long it takes for the building to come back after this way. If it's very tall, it's going to take quite a while, which is good, because it's going to displace a lot. I'm going over here, I'm the tall one, I'm the tower. It's going to displace a lot, a big movement, but low acceleration. While the small building over here is going to displace not too much, it's very stiff, but it's going to have a lot of acceleration, which means forces. So there's a threshold. Don't think ever anymore then short buildings is good and tall buildings is bad. No way. There's a threshold. Short buildings are going to have a massive amount of force because the acceleration, so they have to cope with that, are reinforced masonry, stiff and short. The tall one are going to have the other problem around, a little bit of a, very low forces. I'm not going to break my ankle, but I'm going to sway it so much that if I'm not designed properly, I might collapse. But if I'm designed properly, I will not collapse, okay? Now, the code is written in such a way. There's a nice curve, look at this, fantastic mathematical equation, which is calibrated under thousands and thousands of records around the world. It's an envelope. So there have been thousands and thousands of records around the world, starting in 1940, the famous earthquake in El Centro in the United States, where after that first record, people have been plotting many of these sort of graphs and taking an average. You understand where I'm going? This is what is written in the code, the magic curve, which no earthquake ever will fit. There was actually one earthquake that did fit, which was the first one recorded. This earthquake has been basically plotted by El Centro, which was that earthquake in 1940, by a famous Professor Hausner. He plotted that type of graph, and he went with a curve which was approximating that graph, and that became the law for basically 70 years. Now that you know about that, so you're going to wonder, ooh, hold on. If you're telling me that, let me say in a different way. This is the 500 years earthquake. This is what you design for big damage. This is a yellow to red, okay? You see that? This is where we are in the code. This is a 2011 design for big damage, irreparable. And look at the earthquakes in the CBD. I didn't explain you. This is Eagle Park, with there are 4 recording stations, and that's what the building felt. That's what the building felt. 2 to 2.5, 3 times what was written in the code. Now, having said that, and remember that for a new building, you would expect for this type of earthquake, very severe damage. And for this level up here, this is the famous 2,500 years, you would expect almost collapse. Are you surprised at what you've seen in town? So the question is changing, and your brain starts changing in a different way. You're taking a 1960 car, 1970 car, 1980 car, and now you understand how much they were behind what we are doing today. You try to make a crash test. You're comparing the 1960, 70, 80 car, 90 car with the, they say that the Volvo, not the Ferrari, unfortunately, is the most safe car under a crash test. Okay, let's suppose that that's the best targets. And you're having a crash test, but the difference is that the crash test must be made at twice the speed of what you typically run your crash test, because the earthquake was twice the speed. Would you surprise to see big troubles in the old cars? No. You would actually say, how comes, how lucky we were that not more of those cars could not preserve the lives of the pilot, wouldn't we? And internationally, that's exactly what statistically has happened under such a severe level of shaking. The statistic would have suggested and predicted that Christchurch would have been flat down, much more than what happened actually. So, having said that, let's move one step higher. This is displacement now, is not anymore acceleration. And we said that the tall buildings are going to be subjected by bigger displacement, but they're going to have less acceleration, that's good. But big displacement needs to be controlled. That bump comes from different soil conditions, the fact that we are in a basin area, the fact that the earthquake is not going to fall exactly what we have over there, but just imagine the demand over there, and I do again, where is the code for 500 years, is this one here. This is the displacement that a tower in the city center, any building, a tall one, was expected to have, let's say 400 millimeter, and it became 1 meter. Now, only if you're using the best technology, one of the best from yesterday, you can take it. If your building was designed according to something which was not able to give you that ductility, you cannot take it. So the message is very straightforward. Something which is so severely bigger than the best design that we would do today, obviously could have and should have, and it did, collapse, failed buildings which were not designed at that level. One of the best quotes that we've been using in earthquake engineering from late Professor Tom Poli, and he taught to the world that the earthquake does not read the code. And for how obvious it looks like, the consequences of understanding that are huge in terms of social consequences, in terms of you not accepting anyone to sell you the minimum standard, because you will know that the next June 13, whenever the date will be, we have a friend of the movement to tell when it's going to be. So whenever it's going to be, it's not going to respect the code. We'll have lows, we'll have highs, we'll have bumps and no's, will not be there. The code will be respected in one only situation, which actually is something nice that we like about talking to the seismologist. Should we go to a decent window of time, which is not 50 years, it's going to be 10,000 years at least, or 100,000 years, the whole amount of shake in the Canterbury region is going to be subjected to is going to fit probably fit that curve. Can you see that? That curve is going to be a fantastic envelope in the window, which is the seismology window, and it's not the lifetime window. Now that you said that, I tell you, your brain is going to change so much. Your way of discussing and asking for getting something is going to be dramatically different. Now, that big building, that sort of earthquake, did not read the code, came up with the big bumps and lows. Even the lows were bigger than the 500 years design, so there was a bad news, no matter what type of buildings you were looking at. Stair collapsed, and that was something that the world is now wondering what's going on, because the design provisions, the way of designing stairs in New Zealand are not any different from what they are doing, what people are doing around the world. So there's a quite now severe problems around the world of what can we do. And now it's quite clear. Those stairs are basically nothing else, in principle, seems quite simple, nothing else than elements which are sitting on the top of the landing, here and there, and the length of sitting, because of economy, can't be that much. It came out to be what? Tell me how much you think the earthquake is going to push you for. You saw that displacement, how much is going to push you. Take a coefficient of safety, just think about the worst, and it's going to be a certain number in the 1980. Knowing what the people knew in 1980 in terms of responsive building. So the same approach is happening today, but now we know more about responsive buildings, because there are, I will show you, different way of doing laboratory testing and computer modeling. So already in 2010, the prescription of how much a stair is sitting on the landing are bigger, those prescriptions are bigger than what was done 30 years ago. Makes sense. Still, the earthquake did not read the code, came with the displacement 2-3 times bigger than what it was there, eating up all the safe coefficient of safety, and those stairs collapsed. Now, what is something which is going to be, from a technical point of view, a social point of view, a revolution, and I'm personally pushing a lot for that. We are discussing again about building a redundancy within a building. Redundancy means, let me tell you with a strong Italian accent, how much did you come out with? Make it like that. But that's not enough. It's still the same principle. After you make it like that, then give me a backup plan. Should the stairs unseat, I want to have a backup plan, a catching frame. And I don't trust it. I want to have a third backup plan. I want to have a hanger which is going to hang my stairs on something such that whatever happens, they're going to unseat, they're going to sit on a catch frame. The catch frame will not hold on, and they're going to have a third backup plan. Redundancy is going to be the new old way. It was in the old way of designing, of designing structure. And this is going to be the message, stairs, if we can do something of use for the society, will become, at least we're going to push for that, the safest place that you want to be, not the worst place that you want to be during an earthquake. Wouldn't you expect that? The stairs being the place where you, if you can just go there, oh, great, now I'm safe. How's it going? Still moving. So we can do that. That's the point. We can do that. If you design the stair, and I'll give you an example so you understand what we're talking about, as debunker of our structure, disconnected from the mass of a floor. The stair is a self-standing structure with walls holding the stair only. A gap all the way around, you jump the gap, you are in a very light structure, no mass, that type of stair can't go anywhere, and you're just there waiting for the earthquake to disappear, and then you're going down. You see, technicality is not a big issue, but that's not what has been done so far. The mentality was that the stairs are going to be damaged because, honestly, those stairs are connecting this floor with this floor. And the movement, the big movement, is relatively to one floor to the other. So they're very difficult to design, honestly. It's very complicated. Having said that, talking from an engineer point of view, you don't want to tell that something is complicated. Dubai making towers from reclaimed land. Romans talking about liquefaction and how to do something about it. We are not going to go there, but the Romans managed to get lakes becoming land. So talking about engineering a type of approach, if you ask, I'm not saying that it can be done, but it can be aimed to. And so this is the new ask. People are going to ask, I take it, beautiful buildings is going to cost how much? Okay, 3-bedroom, 4-bedroom, what about stair system? Oh, they're fine. No. I'm asking, what about the stair system? Tell me more about it. So you're going to be the one driving this type of revolution. Facts. Humankind, what we knew around the world in earthquake engineering, less accepted, was basically the same no matter what. In the 1950s, people had the same know-how. In the 1960s and 70s, had the same know-how. Which means that if Turkey, 1994, Northridge, United States, massive earthquake. 1 year after, 17th of January, just 1 year after, in Kobe, Japan, massive earthquake. US, Japan, 2 top schools of earthquake engineering, they were meshed. They were having critical problems in their philosophy of designing. A lot of things changed since 1994. Again, not only since 1970. And then Europe got 1999, a massive problem. And that problem was again confirmed by many, many earthquakes around the world. And from an engineer point of view, which is now you guys are becoming, you're going to receive ad honorem certification for this course, you see through. You don't see that building. You see the skeleton. You see the X-ray. You don't see my body. You're now going to see suddenly if my knee or my ankle are strong enough. Okay, you see through, you start thinking the bone is good enough to take that loading. The legs are far apart enough to take the lateral loading. So that's how we see things. And once you see through the skeleton, ooh, there are troubles over here. Look at here. The legs are bigger than the beams here, but as soon as you go up, the beams are going to be bigger than the column because it was mainly designed for gravity. So the columns are becoming smaller, smaller, smaller. So along the elevation, the column are becoming thin, and you're going to have a pancake, not on the not on over here, but the pancake effect can happen over there, on the top, typically mid height. Plenty of earthquakes in the world showed a pancake collapse mechanism that then caused a progressive collapse, starting from the top, not from the bottom. So these things are well known to be problems of the pre-1970. You can imagine, as we understand now, that after the revolutionary design happened in 1970, the Ferrari was still a 1976 Ferrari, 1980. It was still far away from what we can do today. So no surprises that after you manage to have a revolution, that revolution is still a past revolution. Something else has happened, and we need to do better. Truth and news. This has been tested in the lab way, way before the earthquakes. Obviously, these are walls, according to New Zealand practice, old practice, and international practice, same thing. These are columns in the laboratory. 2007, okay, it's interesting enough, people said, oh, you were testing before the earthquake. Yes, I mean, we did not, as a community, start on earthquake engineering just after the 4th of September. There was enough information in the world since a century, at least I will show you that there's actually much more than that to do something. Now, these are all, the bad news is, all tests according to the principle that humankind had the same know-how in the 1950s, 60s, 70s, and 80s. We were testing the New Zealand practice because people did not believe, obviously, that, let me say in a nice way, Turkey and Italy, those corrupted countries, we don't do like that. So they're bad, but we're doing much better. And so we were saying, no, you have the same know-how. So basically, look at it. All tested in the lab. Beam column joint, the knee, the ankle in a wall. Testing, let me go back. You see this corner joint? is the weakest possible problem of a building, because you're pushing very hard, and in the corner you're really stressing a lot. The knee is going to be subjected to a big deformation. So look at that, and look at what we are able to do in the laboratory. You see here? We are basically able to reproduce in the laboratory the same level of stress. So in the laboratory now, not 20 years ago, we are able to reproduce what the earthquake is giving to us, which means that we are able to design against it. 20 years ago, we were not able to reproduce in the laboratory what was happening, so it was hard to put in the code provisions to go about that, against that. And this video is already the second phase of the test. It's a small quasi-static test, so we're moving slowly, simulating the earthquake, and this has been reproduced at higher speed, and we're getting what the earthquake was giving to us, but we're moving in a small motion. Okay? So we're able in the lab to reproduce things. We're able to do also numerical modeling. The plastic hinge, the famous plastic hinge. That's what happened. We are able to simulate in the very sophisticated computer modeling that type of behavior. This type of modeling was not available in 1980. Not on a computer that everyone was able to use. So you can imagine how much has happened since that breakthrough in 1970, 1980, and so forth, just because of capability of testing. And let me show you something bigger. We've been doing things in the lab, from the laboratory to the biggest test ever happened in open air. The laboratory, what we have in the CBD, is something unique. It's a all generation of structure, all generation of material being tested at the same time so severely. So there are information which the whole world is now trying to understand. Unfortunately, most of them are not news, are not novel. Not novel. Have you seen what we've tested in the lab? Sorry. It was all part of, I was using different slides in my course, using different type of earthquakes in the world, and they were not novel. So that's not a good news, because it means that New Zealand had the possibility of learning it and implementing it. Why did not happen? Because we want to have the cheap solution no matter what, and because we don't think that the Alpine fault will ever happen, and if it does happen, we're not going to be affected. Vertical acceleration punched through very heavily, and that gave a lot of troubles which were unexpected. So there are a lot of new lessons, unfortunately, learned by this earthquake. And what we've been working on is preparing a report which is showing for all the buildings that we've been entering, basically more than 100 damaged, with different red, typical, obviously you don't enter green buildings. If it's green, there's not too much damage. You need to report the damage to try to understand something. So we were entering the yellow and red for the pleasure of my wife, who was telling me, are you sure? Luckily enough, she's an earthquake engineer too. So I was getting my father, who's an engineer too, telling me, I understand that you have to do it, so go for it. And my mom, I don't understand it, why you have to do it. At least we see that this is valuable, and I can tell you it was quite a pleasure after a few weeks to remember that, I mean, as an Italian, you like to put a jacket and a tie. And so I did remember that we had a jacket and a tie, not only a hard hats and everything like that. But these information are becoming of fundamental use for the highest decision making. Only if, again, you guys that are aware of it are going to ask for some changes. Now, can we fix these existing buildings? First of all, can we fix them? The answer is possibly yes. If you ask, it can be done. I received a phone call, it was quite interesting, from someone, a journalist, not the same one, asking, we know that you have, you're holding a secret report, confidential report, on existing buildings, vulnerability of existing buildings in New Zealand. I say, yeah, www.retrofitsolutions.org.nz. It's so secret that it's on the web since years, 2004, and has been funded by the government. And the Foundation of Research and Science and Technology founded a project called, look at the magic, the project was called Retrofit Solutions. It was not called, please check whether it is really true that our buildings are vulnerable. It is, please check how we can fix them. Did you know that? No. You know why? Because once something is on the public domain, there's basically no value. And I can prove it because as soon as we prepare a report and we put not for public, highly confidential, it went to the highest level in half an hour. I don't understand how that could have been possible, but basically we got the point of talking to the highest people. Problem being that because it was not for public use, you people did not know it. Now that you do know it, and you know approximately, forget about the technicality, what the higher people decision making, can you stop the recording? know it. Now, this is where the revolution can happen. You can ask and demand a request, and we're going to give you some tips on how to do it. Now, in the lab, because of this major project, we test solutions, carbon fibers, post-wrapping. If you need to fix your knee or your ankle, you wrap around. The new way of wrapping around is using high advanced materials, steel fibers or carbon fibers, which has been used for decades in our space industry, and then they came down to the more normal aircraft industry, and then they came down to civil engineering. Now, this is available in a way that 20 years ago it was not. It was too expensive. Now it can be done. Another type of solution, including walls, look at this material here, made of different things, and I'm going to discuss a little bit later about what can be done. Now, who told you that strengthening is the way to retrofitting? And I'll give you an example. If you have a problem with your knee, and the problem of your knee is that the connection of your tendon is not properly done, your doctor, which happened to me, is going to suggest you, it's okay, I'm going to cut your tendon and then no, you don't cut it. I said, no, I don't like it. You don't cut my tendon. What if you're not able to reattach it back? No, that's the procedure. So I didn't like it, I didn't do it, I didn't fix it. But now I understand what he meant. And it meant that for strength retrofit, you don't need to increase the strength. This is what you've seen, haven't you? Right? Typically it is Turkey. Now we can unfortunately use New Zealand too. This is what you can do. Saw cutting, cut the base, cut along the height, make that massive wall, which is going to try to break in shear, something which can lift up from the foundation, if you cut at the base. These are typical interventions done in marble blocks in monumental structure, okay? Now, people told me, sorry, you're missing a slide. You should be showing after the test. That's after the test. This is the same bad old type of walls that can fail badly, dramatically, because it was not designed to take lateral forces. And then you allow this wall to just step up and move and displace. And you're going to add a little bit of a protection. These are basically nothing else than bandages at the end, such that the concrete will not push out. Done. This is the level of damage that you would get after fixing. How much do you think that cost? Nothing. Number one solution, which is probably going to be adopted in the L'Aquila earthquake. You have already a wall in your structure, use it before the damage, and try to make your structure behaving in the best possible way that we can do it today. So don't buy someone telling you that retrofitting is going to cost you too much, because it is true if you were using the 1980 way of doing retrofit. This has been developed in the last 5 years. The better news is that progresses have not been done only in strengthening, in bandaging, in medicine, in surgery intervention, okay? I think about from the medical point of view is the same concept. As a structural engineering, our patients are not our body, but are those structures. So in new technology, now you believe us, I'm quite sure that you do, you're going to tell to someone why you're using the same old way, the best old way. Now you can use the best new way, okay, because things have improved. So let's see how much. And to see how new the best way is, let me tell you a story, because I'm very much proud. Before becoming an engineer, my father was an engineer, and I wanted to be like my father. He tried hard to tell me that I should have done something else in my life. And the more he was telling me, the more I was taking up the challenge, saying I'm going to do it. And then eventually, this is something that I will not be doing with my son. I will be going to do the same, the other way around, telling him that he must be an engineer. I will be very proud if he could continue being an engineer. And one day he would come to me telling me, Dad, you know what? I'm going to do what I want in my life. And I would say, yes. And I say, please go ahead. Now, before becoming an engineer at high school, there's quite an interesting high school path in Italy, which is the Lyceum, the old way from the Greek. It's a high school on humanistic studies, where you're studying Latin, you're studying Greek, ancient Greek, you're reading the transcripts, so you're learning unbelievable things about philosophy of the Greek and way of doing things. Now, Sparta, those few years ago, earthquakes were there. We did not invent earthquakes, unfortunately. You know, they've been there. A little bit low, these I'm using just for the pleasure of showing that people have been dramatically emphasizing the damage of earthquakes in the past. Earthquakes have been with humankind forever, because we decided that mountains are nice, and so it's quite nice to be in a region where all the bullet points, those yellow and red, are going to happen. So that's what humankind decided to be. And you see the dramatic solutions. Bell towers are actually falling apart. Liquefaction does happen, more dramatic than what we think. Tilting of elements, it did happen since ages, so there's nothing absolutely new in that. There's a good way of taking towers when they're falling apart and replacing into new apartments. That's Pavia, my city. It was called the city of the 100 towers, medieval towers. It's not a seismic area, but a few of them came down because of age. And the best way of refurbishing those towers, which was 3 times as tall, is actually to make it becoming an apartment. And you can bet that he's not an engineer, nor an engineer academic owning that. He's a lawyer. Are there any lawyers here? That was supposed to be my path that my father was suggesting me to go. Now, 2,500 years ago, this is still considered the best way of resisting to earthquakes. 2,500 years ago. Ancient Agora, in the Acropolis in Athens, they were using big marble blocks. They could not use steel. They did not have steel. So they were putting marble blocks on the top of each other. And under the earthquake, those blocks were doing what? They were just rolling or rocking on the top of each other. We are able to see this structure there since after 2,500 years. The Romans picked up the theory and they understood. They made a little bit of a small, slender type of construction. These are the Fori Romani in Rome. And the type of mechanism, this rocking, was happening at the basement and on the capital, just underneath the capital. They were able to sustain earthquake loading, and that's what you can see. This is one of the most beautiful preserved Doric temples in the ancient Agora in Athens. And the concept of earthquake resistance is so simple, which almost looks incredible. They've been taking centuries to develop it. Blocks on the top of blocks, that's the big mass of the temple. It's shaking back and forth, and your temple is doing nothing else than this type of movement without breaking. Those blocks had lead casted into in the core to allow, when you do this type of motion, you can actually slide. To prevent the sliding from happening, they were casting lead inside. And during the First and Second World War, people went there to pick up the lead to use it for military purposes. But that was basically the sheer key. Look at this. New 1990 to 2000 type of technology for bridges in the United States, Olympia, where the Olympic Games are coming from. And I like to call it the bridge of knowledge. We are just copying, it would be brilliant if we were able to copy from our ancestors and improving it. Very often we just start from scratch because those poor fellows did not have computers, so forget about it. And now we're rediscovering how brilliant minds they had and how we can improve it. 2,500 years later, and that's the novelty, that's what we're able to do. Same concept. These buildings are everywhere around the world. There is one building in Caledonia Street in Christchurch, which has been designed with using this improved technology. And basically we have 2 good news that we can provide. Key we made, base isolation, and all of you might know about that. Base isolation is this way of putting basically your building on a skateboard and on rollers. And the earthquake is shaking underneath, and you just stay almost in the right position. If you were making a frictionless, no friction at all type of roller, basically you would not even feel the earthquake. Can you see that? In the future, please take it as a joke, but it's not a joke. I really believed when I thought that I can do something in earthquake engineering. In the future, the best way to avoid to not take the earthquake is going to be what? This way. Okay, so the earthquake comes, you jump, and then you come down. How can you make it? You know how the Shinkansen train is running in Japan? They're basically using, let's say in a nice way, a magnetic field which has allowed you to be a little bit separated from the surface. In the future, it's going to be possible to trigger an early warning, few seconds. You're going to use not too much energy to just push the building up a little bit. A magnetic field can have a humongous power, and then you're sitting there down. Write it down, because I'm quite sure that if my son trying to please me is going to go for engineering, I'm going to hope that he's going to develop that. First of all, base isolation. You have a question, how much does it cost? I'm going to tell you not that much. How much? Not that much. Equal to cost market. After the L'Aquila earthquake, 20,000 people were accommodated in brand new 3-story apartments. Brand new means almost a passive house, best type of technology for insulation, best type of technology that you can use today. And they were using a basement underneath to have cars. What a brilliant idea, because as soon as you do that, so basically, what you're creating, let me explain it, is you see just on the top of the column, you're having your rollers. You're using on the top of your column your isolators. But you're saving the money of the base isolation by using the basement as a car parking. And I think we would agree that car parking is an issue in any country, isn't it? And if a water table is a problem, engineers are going to solve that problem. It's not a big deal. So the cost of these houses on rollers, these are sliders, are different type of things. 20,000 people in 3 months from the earthquake in April. Between 3 months and 6 months, people were in these top houses, which are absolutely brilliant. And that's what they look like. Concrete, timber, steel were all on the top of a massive platform which was isolating the houses. Can this be done for New Zealand? Of course. Why it has not been done? Because you people didn't know. Now that you do, you're going to ask, you know what? I wouldn't mind to have that type of solution, which I know this doesn't cost too much. And it's going to be top-notch. It's not going to be a temporary accommodation. It's going to be a brand-new top safety type of things. On the top of the big platform, you can have any type of material you wish, any type of concrete, timber, or steel. How does this work, this technology? The base isolation is one thing. The revolution of the Greek temples happens in the form of something like this or something like that. And to show you what it is, this is the Greek temple. Have you seen the walls in town? Have you seen how much damage they got as soon as something was trying to shake them? All over here? They don't need to be damaged now. They are using the Greek marble rocking technology for which they are moving, they're coming back to the original position. No damage. You've seen the temple over there, 2,500 years. We don't have to convince you, do we? What is the new way? They did not have steel. Now we do have steel. So we are putting a high, this is a steel rod that we are using for construction, typically in pre-stressed concrete. This steel rod is going to be pulled and is holding such that I can decide when this is going to move. So it's not going to be very floppy. I can tune it, pull it, and it's going to be very, very robust. But should the earthquake come bigger than what I designed it for, it's just going to rock with no damage. You cannot damage it. Okay? And since you don't believe us, we have the equivalent solution for, it's the same thing. What I haven't told you is that these guys implemented the same technology. It's elements which are able to rock, and there's a rod going through, and if you were coming over here and tying the rod, the more you tie the rod, the stiffer this becomes. But if the earthquake comes very strong, you don't break it. It's marble, it's moving. It's not monolithic. You can't break something that is not connected in a monolithic way. You can see that? So the revolution is the same thing. These are a little bit of a scale model we're using for teaching. Humankind tried hard to redevelop this solution 2,500 years later, and it's being called LEGO. They managed to patent it because after 2,000 years, the patent from the Greek expired. Luckily enough, they did not patent for construction. So this is free of charge for all of you, free of charge, is in the public domain. You just ask, they might give you. And to tell you how much is the public domain is, old ways, best old ways. You get an earthquake, you know this now, you do it, right? Damage, accepted, is in the code. That's the best that the code will, so the minimum standard the code will tell you when you have a monolithic type of construction. This can be concrete, can be steel, can be timber, don't get it wrong. Plastic damage is going to be in the old material. New generation of rocking temples. Can keep on going, can keep you here for hours. I love it. Now, 1970, there was that major revolution saying, if we have plastic hinges in a proper place, we are going to avoid pancakes. So we did this type of experimental test, training our engineers. The only way is to have education everywhere. So we are training our engineers, our students, in looking at what happened if you were doing it the old way. Let me say in a different way. What happened if you do not strengthen an existing building, which is itself very vulnerable? Who cares if the Building Act is not enforcing you to do so? Now you know it. It's not anymore. In Wellington, they are getting very scared. They are actually strengthening without waiting for changing the use. Now that you know it, you just do it. Now, present is damage which is happening here in the plastic hinge. But it's damage. You are not happy about that. Not yet. The new generation is a revamping of these rocking elements, okay, these rocking elements, which are able to, instead of getting damage, just to roll a rock back and forth, and after the earthquake, they come back to the original position. This is in the code, is codified, can be designed. What is the next level up? You can have fuses everywhere. Basically, imagine reinforced concrete. Typically, you have seen bars inside. Bars do not have to be inside anymore. We can have bars outside, and these bars are what we call fuses, dissipators, of any sort. That's it. We call it plug and play. We've been developing them. You can plug them in and play. During construction, it's so simple to add them on. After an earthquake, if you damage them, you take them away. This is the earthquake engineer that we are pushing for. It's so simple and cheap, cost effective. That is absolutely unbelievable. And how simple it becomes. You see this plug and play between beam and columns? We've been testing all of this, and they don't get damaged. It's basically boring because you keep on going and nothing happens. And when you publish something in literature, you're getting a review telling you, excuse me, can you actually show us the real experimental test, not the ideal one? That's actually the real one. So people don't trust you. Big aftershock. In Countdown, there's going to be a new section, which is the seismic shop. You're going to go there. And there's going to be a 2x3 discounted, this called yielding device. But there's going to be also a viscous damper. Oh, a viscous damper, I always wanted to have one. I'm going to wait for the 40% discount. Okay. Now, what do you know? I have to tell you, but again, it's a pity that I had the pleasure to be sitting on the plane when I was coming down with Jerry Brownlee. It just happened. And I told him, oh, it's great, because now for 45 minutes I'm going to make you feel sick. It's not going to be, it's not going to be the bumping. Now, it's been very accommodating, because basically I told you, the problem is that today I'm going to have a public lecture. I'm going to tell them that they can have the best technology, and they can have a special section, a special sort of a discount, subsidized by the government. Why not? Why can't you ask? Why can't you ask to have the new revolution of of double glazing? This is the one. We want to have those type of stuff. What is the name? Temples, new temples. How much does it cost? I don't know, but can you please enforce it like you did for the double glazing and the heat pump? I changed my heat pump too. I got it. And we would like to have the same approach. He liked it. He said, we are going to consider. So now that you know it, you can be the one, and it's the right time. If I'm not wrong, it's the right year for election, isn't it? To ask to who you're going to elect, what is your big plan? Significantly big plan. After L'Aquila earthquake, the government came down with 40% of tax reduction for strengthening of your building. Don't you think it's appropriate? So I would call it, let's take it nicely, stick and carrot. Honestly, only if it's enforced, stick. And then you give the carrot incentives, it can happen. The same thing happened in Italy in changing cars. The government came down with a huge revolution saying, if you change the cars within the next 6 months and you're going from your old type to this less polluting type, according to European practice, we're going to give you, the incentives were absolutely unbelievable. People that didn't need to change the car, they changed the car. They finished the funds. It was such a successful improvement that they roll it over again and again. Basically, in the 2-3 years, there's been a complete change from the best old to the best new. And guess what? This type of technology, and I'm going to tell you, can be done in timber, concrete. We've been developing in timber. These were toys that we were using, as you know, for any cathedral design in the world. People were using a lignum, a wood type of model we've been using to show concrete. Then we thought, why don't we do in timber? It did happen. We have buildings in timber using this technology. We've been testing that, and my colleague, Professor Buchanan, is going to speak something about this tomorrow, and it's basically using the same concept. You can use both of them. Plenty of tests in the world, follow through, because we have to finish here. Experimental testing, significant one, and this is quite nice. A huge testing facility in San Diego, in the University of California, San Diego, that Kiwi professor Nigel Priestley, legacy from New Zealand, developed this new concept. Can you believe it? It's all about New Zealand legacy, and you're not going to use it. Doesn't make any sense. That still tall but much younger guy, it was myself, not trying to jump down, but they were trying to show that there was an international. Can you understand it? Can you hear my accent from over there? I don't think you can. And I told them that it was a wrong political decision because I'm so tall that the building looks small, but that building was huge. Test in the lab. What is happening is, what we're missing, to be honest, is that we do our testing in Canterbury University. We don't have that big facility. So for how much we're trying hard, I was actually very pleased to hear, we are all very pleased from the structure geotechnical class that we hear that the government is pushing for a new, have you seen that, this Earthquake Information and Research Center? After big earthquakes, 1995 4 in California, 95 in Japan, there were big facilities to test because you can't keep on testing what we call toys. You have to test something similar, of different big size. 39-story building in San Francisco. San Francisco is basically like Wellington, says Misty Wise, is using this technology. Just to tell you how big you can go, how tall you can go. Now, just to tell you, take a prejudice away from you. If you have a not good foundation, because you are sitting on a not good soil, we do know that trees, the taller they are, the more they like to go down with roots. A tall building would naturally need piles. And it's easier to go down 40, 50 meters for a tall building than for a 5-story building, isn't it? Now, is actually tall buildings better or worse in terms of foundation issue than a smaller building? If you really need to go deep and not having problems with liquefaction. I leave it with you, but it's quite clear. South America, Italy, we develop all of this. All of this does exist around the world. And there's one reason for which the world is changing into this technology, which is cost. No one as a company buys something or develops something if they don't make money. So just believe that there is a reason. And we managed to show that the costs are low even in New Zealand. University of Victoria University is using the brand new, you see this plug and play? These are nothing else than what I showed you. We used in New Zealand just a few years ago the best so far of this technology, which we are still developing. And then it came the big earthquake test, because the second building was actually designed in Christchurch. Is using different type of things, is using this technology. It costed less than the traditional solution. The client was Southern Cross Hospital. They were very happy for us to propose something new, as long as they did not have to pay the risk and they did not have to pay the cost. So after the earthquake in September and after the earthquake in February, you go there, and that's the level of damage. There's a zoom, big zoom, that you can see over there. It's part of the progress, like we call, and that's what you get. That photo, nicely enough, was not taken immediately after. You can have something moving, but it was operational immediately. It was basically used immediately after for major issue. Now, how is it possible that this new technology costs less? And let me just give the most obvious example, if I can find it. You would have it yourself. You remember the first mobile phone from Motorola? Now, how much did it cost when compared to not the best one, but the one generation behind mobile, obviously? Let me tell, so it's clear, it costs less. Would someone of you ever bring home a 1980 IBM, 1984 IBM desktop? I'm going to pay you to do that. You're going to say, are you idiot? Sorry. You're Italian, we don't do that. Say, no, I'm going to pay you $100, you bring it home, you use it for your work. Now, why, if we now believe that building technology has evolved not as fast as IT technology, but pretty fast, why do you believe that something of this nature is going to cost more? Now, I'm finishing off here, and this is the last one, so spot on time, no question and answer. Isn't this the good news that you should be receiving? Now that you know that they are available, then you can ask. Now let's see how much dramatically the change is going to be, your change. You're going to go home, start talking to people. Your insurers is going to tell you that there's no way that they're going to pick up the bill anymore. And you're going to tell them, I have a new way. You don't know it, but this new way is going to give no more damage. Oh, it doesn't matter, it's Japanese. No. It's South American, Italian, US, and Kiwi North Island, Kiwi South Island. It's there, you can go and see it. How much does it cost? Don't worry. I'm going to have that building, and you play the game. I'm going to pick up the bill for a better technology, but you give me a big discount on the premium, don't you? Of course I will give you. So you're going to have a building which is going to cost less. You're going to have a premium which is going to be less. You're going to use that premium I just suggested that can be used for a big levy at the government level to pick up the bill to promote new technology and then paying you back for what you're able to do and having a massive amount of new funding for the development of new infrastructure, because they're going to save significantly from insurance and so forth. So with this one, thank you very much for your attention. I hope that I managed with my mission of changing your mind in a way and making you becoming the ambassador of the revolution that you're going to drive.